Hello everyone. Today I will talk about one-way quantum computer published in 2001, 2000 in Physics Review Letter. The reason I choose this paper is that I'd like to introduce other quantum computing techniques other than circuit-centric quantum computing. If you're familiar with Qiskit, you think that you think that quantum computing is just classical computing with special rules that enables to solve certain problem exponentially fast, but that's not true because there are other types of quantum computing such as quantum adiabatic computing and measurement-based quantum computing, which is based on the one-way quantum computing. Yeah, so I would like to introduce that kind of other types of quantum computing skills. Key is to use the entanglement as much as possible because entanglement makes quantum computers fundamentally different from classical computers. Cluster state is, you can think of it as a qubit that is maximally entangled quantum state. So we prepare initial state in this kind of product state, which is not entangled. And we can evolve this state with this interaction Hamiltonian. This looks like Ising type Hamiltonian. The resulting cluster state is like this. This cluster state has property of satisfying this eigenvalue equation. So the eigenvalue can be either plus one or minus one, depending on the configuration of qubit layers. Here, NGBH means the neighborhood of qubit A. Okay, so if we have a cluster state discussed before, then we can measure qubits on Z basis so that we have this kind of state. Here, N means unmeasured qubits, which forms a network like this. Before we go into any more details, let's look at this figure. So the dots is actually error coming from the screen, which represent the measured qubit on Z basis. And this vertical arrow represent qubit measured in X basis, and this tilted arrow represent the qubit measured in XY plane basis. Yeah, so this network cluster state is similar to original cluster state of the local unitary, depending on the measurement value. And also this network cluster state satisfies this kind of eigenvalue equations only with different eigenvalue. So we have a wire or network. So let's use this network to do some quantum operations. We can measure unmeasured qubits in certain order and basis depending on which operation we want to do. Horizontal wire represent the flow of information, and vertical wire is used to implement 2-qubit quantum gates, which I will explain in later slides. So we perform some measurements like this, and at the final state, we choose a measurement base or readout basis to read out the qubits. Important thing to notice here is that we only use 1 qubit measurement. We don't really need to implement a bell-based measurement, which is kind of hard. Another property is that when we usually think about doing quantum operations, we usually increase entanglement and do some non-local operations and then measure, right? However, in this one-way quantum computing, we first make a huge entanglement, right? By making a cluster state, and we measure its qubits, so the entanglement decreases. Also, that's the big difference between measurement-based quantum computing and circuit-centric quantum computing. So let's see some examples. Here is how to propagate information. We can prepare this kind of state, right? We have all 12 states, and we'll discuss about this initial state later. But let's just say this is possible for now. And we perform entanglement as we discussed before, and measure all qubits except for the last one with X basis. Then we have this kind of state depending on the measurement result. And it is interesting that initial state and output state is equivalent of the local unitary, which is this. We can actually calculate use sigma, which is either identity or Pauli xz and xc operator. We can calculate use sigma with only 2 bits, which is the output of our measurement result. Okay, so using this, we can implement single qubit gates. Here is a general representation of single qubit gates. For some who don't know about Blow-Spear and single qubit representation, here are some figures you can understand that help you to understand. A single qubit gate is essentially the rotation on this kind of Blow-Spear. We need to know theta and phi, and also there's one more parameter which is global phase, but it's not shown here. But okay, so we need 3 parameters to make a general single qubit gate, and that can be transformed into Euler rotation, which is represented in this kind of way. So anyway, we need these 3 parameters. Okay, so let's go through some procedures. So we prepare this kind of initial state, which is very familiar. We need 5 qubits here, and we do entanglements. And after entanglements, we have this kind of state. You can just calculate with pencil if you like. And we measure qubit 1 to 4 using this kind of basis. Notice that this basis is on XY plane. And after measurement, we have this kind of state. So initial state and output state is same up to local unitary. So what is this unitary gate? For simplicity, let's just choose alpha 1 as 0. So the measurement basis here is just measured in X basis. Then unitary gate is in this form. So this is general single qubit gates, and these are some auxiliary gates which we can take care of because we know all the measurement values S1 to S4. If we want to implement this general single qubit gate, we prepare an integral initial state and measure qubit 1 in alpha 1 equals 0, and measure qubit 2 in alpha equals this, and measure qubit 3 in this basis, and measure qubit 4 in this basis. These numbers, right? So minus 1 factors are all cancelled out. So we have this kind of unitary gate implementation, and we can take care of this auxiliary rotations at the end of the computation, which I will discuss in later slides. And so we know how to implement single qubit gate. So let's implement Sigma gate, which is most famous 2 qubit gate. For the people who don't know about Sigma gates, Sigma gate is this. Sigma gate is this. So depending on the control state, we can flip the bits of target state. So the output state is representing XOR operation. So in general, we write Sigma gate in this form. Okay, so let's say initial state is generally I1 and I4, and same as before, we prepare other qubits in plus state. Here we need at least 4 qubits. In this kind of configuration, we again apply entanglement as before and measure qubit 1 and 2 on X basis. Then we have this state. Okay, this is XOR operation, so it means that we implemented Sigma gate. It's that easy. So here we need to consider about this auxiliary rotation. So this is the 2. I will say this is 2. It's a product of state 3 operation on state qubit 3 and qubit 4, but it's a product state, so we can easily take care of. Before we saw how to implement Sigma gate, but in general, usually our target state and control state will be far away, right? So using the information propagation, we can generally construct CNAT gate using this configuration. And well, the detailed operation would be different, but basically it would be the same. We use measurement output to make our target state. To give more details, with general single qubit gate and CNAT gate, we can make a universal gate set. This is not a specific proof, but we can say that measurement-based quantum computing is actually universal. Yeah. We assume that creating any initial state is possible, but actually creating this kind of initial state is very hard. But using this single qubit gate scheme and CNAT gate scheme, we can implement any arbitrary initial state, right? So we apply some single qubit gates and CNAT gates to make a general initial state. Okay, so that's how we make initial states. And for compensating auxiliary rotations, using this relation, we can see that auxiliary rotations can go to front or go to back. So we can just keep making the auxiliary operation forward. And at the final measurement, we can take care of that auxiliary rotation into measurement basis. So that's how we take care of U sigma. Up to now, I discussed some main ideas on this paper, and I'd like to do some discussion with you guys. I have some questions, and if you have any insight, I'll be glad to share this video. Okay, let's do some discussions. So my first question is that what kind of physical system we can use to implement one-way quantum computing? So in the paper, they said it has been already implemented in neutron atom potential lattice and 3D photonic lattice and some quantum dot system. So what do you think? What would be the other physical systems we can use? Spin wave. Can you explain more about spin wave? Let's move on to next discussion topic. Do you think auto connection is possible in this one-way computing? Because if you consider 3D lattice, we can make a 2-qubit gate wire over the information flow wire. So do you think it'd be very easy to make that kind of 3D auto connection? And how about other benefits compared to other quantum computing systems?
Maybe since we just need to prepare a nice state and just measure it properly, it will be prone to less error than maybe gate or adiabatic computing.
How about other opinions? Odin said, yeah, using only one qubit measurement is a very huge benefit. That's right. And let's move on to next discussions. Up to now, we consider a square lattice or cubic lattice, but how about what would happen if we consider a different kind of lattice out, such as closed pack structure? The number of neighboring qubits would be increased. So how would that affects the result? Any other questions or other opinions? Okay, if you guys don't have any more questions, let's end this meeting.